pleased to introduce the speaker for this session, Pierre Baque. Pierre received an engineering degree in applied mathematics and a master's degree in operations research from Ecole Polytechnique in 2013. After working in algorithm development for Credit Sweese in London, he joined the Computer Vision laboratory at Ecole Polytechnique Fédérale de Lozan. He finished his doctoral degree in early 2018 under the supervision of Professor Pascal and Francois Fleuret. His research focused on deep structured learning and variational inference applied to computer vision and CAE. During his PhD, he published multiple papers in top-tier machine learning conferences. After his doctoral thesis, Pierre founded Neural Concept in 2018, where he is currently working as CEO. It will now be our pleasure to hear from Pierre Baque.
Hello everyone, my name is Pierre Baque. I'm the founder of Neural Concept, the software that makes it possible for engineers to run 1000 simulations in a day and to design 20% more efficient products. Please, let me tell you about our story. 120 years ago, the Wright brothers made the first successful manned aircraft flight in history. The prototype was far from the planes used 40 years later after World War II. This evolution was possible thanks to the efforts of millions of engineers who created and tested thousands of prototypes. Each one of these costly iterations helped engineers build a better understanding of the behavior of the aircraft and derive some general rules. These rules and intuitions would then be used to guide further design iterations. Starting from the 80s, the usage of numerical simulation in engineering became more and more widespread, boosted by the availability of personal computers. Numerical simulations are now used in every field of engineering, ranging from nuclear physics simulations for the control of energy reactors to the simulation of blood fluid mechanics for the prevention of heart attacks. As we have entered the 21st century, simulations have become ubiquitous to engineering, but humanity is confronted to new, seemingly unsolvable technological challenges. One hope is that with the help of a computer and complex algorithms, engineers can achieve radically better performance than what he would do using only his intuition and simulations. Today, already, these optimization algorithms created 50% lighter parts for an Airbus plane or a 20% more energy efficient drone. Neural Concept provides engineers with the right tools not only to evaluate man-made designs, but also to guide them and create better performing ones. With the help of a computer, an engineer can achieve radically better performance than what he would do only using his intuition and traditional simulation tools. One of the core difficulties is the fact that numerical simulations are very slow, and, like a human, an optimization algorithm needs to test its hypotheses and to simulate them many times. Therefore, an alternative is to introduce a third algorithm, a neural network, for instance, that is a proxy to the simulator, that runs extremely fast and that makes it possible to explore millions of possible designs in a day. More than a century after the Wright brothers, nowadays engineers are faced with radically different and new challenges. Neural Concept is working with industrial leaders across the globe, such as Airbus, Safran, or Bosch, in order to allow for widespread adoption of new algorithms and making sure that we can meet the challenges, for instance, of making an electric or hydrogen-powered plane make commercial flights across the Atlantic.
This is a team of Neural Concept that is working on developing this concept relentlessly every day since more than 4 years. Neural Concept is the company that I founded. And today I'm going to start this more detailed presentation about what we do with a very nice and inspiring example for a sports example and a world record. So actually on the September 13th, 2019, two riders, French riders from the same team, broke the two world records in two categories for human vehicle speed world record, breaking the previous benchmark by a wide margin. And so they went like, for instance, the bicycle went to a speed of 136.7 kilometers per hour. And this tremendous improvement and tremendous speed was by large attributed to some extent to the external aerodynamics of the hull of the bicycle. How did this happen, and how was this made possible? So Guillaume de France, who is normally who is the team manager and who was designing the external aerodynamics of the bicycle as well, was usually working and iterating with a team of CFD analysts to whom he was sending design proposals, and we were coming back with optimization, with CFD results and optimization proposals to Guillaume in order to improve the bicycle. However, as the time was getting tighter and tighter, and Guillaume was getting close to the deadline for completing the project, the different constraints and different situations were entering into place. For instance, changing the rider, new gear system, new size of the wheel, and so on. And all these changes had to be taken in very fast, very quick amount of time, making it also difficult to keep the design optimal for the bike. And that's how we started working with Guillaume to introduce a new workflow, a new design approach, where instead of working directly with the CFD analyst team, Guillaume was working with a centralized system, which was an AI system, learning from the data produced by the CFD team. But Guillaume was able to interact and interrogate directly the AI system to get optimization and simulation results in a very, very quick and fast manner. So how did it work, and how was that possible? The core technology that Neural Concept is using in everything that we develop within our product is mostly based on deep learning. Deep learning is a quite old technology based on neural networks, but it really started regaining interest in around 2012, where it started completely redefining benchmark in image processing and in natural language processing. And progressively, it went to also revolutionize other domains of computer science, ranging from games to 3D reconstruction. And nowadays, we see a very interesting trend since in the last few years, where the deep learning is also completely changing the way we think and we design the physical world, starting from generative design for molecular discovery, and now having a tremendous impact in the domain of engineering and CAD/CAE. So what is really different about deep learning? So many things are different compared to traditional machine learning algorithms, but one key element for me is the way the data is processed. In traditional machine learning approaches, the data is input to the learning system in a completely abstract way, using a set of design parameters or a set of parameters that will maybe represent personal information such as age, sex, or city for a person, but it can also be the number of occurrences of words in a text or a set of design parameters, and the data will be represented in the same way and processed almost in the same way. With recent algorithms, starting from convolutional neural networks for images, the trend has been going in the direction of processing the data by respecting the physical structure and the physical nature of the data. For instance, if you are learning from an image, the structure of the algorithms that you're using for processing the image will be in accordance to the 2D nature of a pixel of array representing an array of pixels representing an image. If you're processing text, you will use recurrent neural network structure that is also respecting the structure of sentences and words in a text. Similarly, if you're processing information from a molecule, you might want to use graph neural networks that are also taking into account the physical structure of the graph representing the molecule. And similarly, in engineering, if you process a 3D geometry, a CAD represented as a mesh, you can use specific algorithms that will respect the physical structure and nature of this 3D mesh. One of the core and typical things that we do with at Neural Concept is to emulate and to learn to reproduce numerical simulations. So typically, we will take a data set of simulations represented by pairs of CAD geometry and simulation outputs. And then we will learn to reproduce the output of a numerical simulation without actually running the numerical simulation, directly starting from a raw CAD geometry. Another example of what can be done with these neural networks is to recreate a 3D geometry directly from a drawing, a sketch of a vehicle or of a geometry. So in this example, it's an example with car design, where a designer can sketch in 2D from any point of view the geometry of a vehicle that is regenerated in 3D. By coupling this with the example that I showed before, with the ability of emulating the numerical simulations directly from 3D, it is possible to chain these two modules and have directly aerodynamic prediction from a sketch, as you can see in this example here. This is here an example of how the tool developed by Neural Concept works and how an advanced scientist can use this tool to analyze and validate the prediction of a neural network. And in this example, the expert is comparing the prediction and the simulation for external aerodynamics of side view mirror in automotive design. And we see that here on these examples, we can get quite close, very arbitrarily close actually, to the real simulation. Once these predictions have been validated and that we have actually checked that the simulation and the prediction give sufficiently close results, these predictions can be coupled to a CAD system to get instant simulation results directly from the geometries generated and designed within a CAD system. And here it's an example for a cold plate design for cooling electronic components in a satellite panel. But this is also applicable to cold plates in the automotive industry, for instance. In the context of our partnership and our collaboration with the company Orbital Stack, which is a subpart of RWDI, we have been able to learn from a very large data set of numerical simulations and of physical experiments for pedestrian comfort analysis and external aerodynamics in cities, and built a predictive model that is able to give instantaneous results of different configuration of external aerodynamics on cities, while getting an accuracy that is similar, that is very close and sometimes even better than runs analysis that normally take hours or days. And this is really a revolution in the way designers can design and the way architects can think about the external aerodynamics and the pedestrian comfort in cities. Once you have trained this very fast and very efficient surrogate model, they can also be used to suggest and to generate optimization, to suggest new designs for the designer. And here in this example, we are using a motorsport application where we are trying to find the best configuration of the front wing that will allow to generate or to remove some specific vortices behind the front wing. In the previous example, we are optimizing directly in the space of the CAD geometry, so modifying directly the CAD geometry, but it's also possible to modify and generate directly in a much more free way a 3D geometry, and here completely changing the topology of the design in an arbitrary way. So doing things that are similar to topology optimization, but with a model much larger and much faster scope of views as well. So we see that this is a very powerful technology with a lot of potential, but how can actually engineering teams leverage this technology today? So first, we are today seeing that in engineering, everything is about solving a trade-off. A trade-off between the need to get always better performance, which means also considering the performance of the design and the physics earlier and earlier in the design process. And also the need to, and on the other side of the trade-off, the need to shorten design cycles, which means reducing iterations between design teams and simulation teams, which are actually quite often one of the core bottleneck of this process. So the simulation tools that have been developed and deployed over the past 20 years have helped a lot in reducing the risk of failures for prototypes, in improving the product performance, but they have been quite short at delivering on the side of day-to-day analysis and helping designers come up faster to with better design, leveraging on the knowledge and the data from within the company. And this is exactly what Neural Concept to do. So exploiting the concept of engineering intelligence, that is learning and swallowing all the data that is generated within the company related to design and simulation in order to produce and to simplify design workflows and make them very fast and very accurate and accessible to any design engineer. So we are moving from a paradigm where we have on one side the simulation team, on the other side the design team, and they are iterating by exchanging files, or even like using a centralized system, which is like very time consuming and allows to the iterations that will be taking maybe 1 week, to a new paradigm where the simulation expert is also becoming a data science expert who is able to train and validate neural network models that are then deployed to simulation teams, which will then be able to run their simulation and optimization workflows in a very fast manner, so within a minute or within a few minutes, and also do this completely independently from the simulation team. Of course, the simulation team will sometimes have to be brought back in the loop in order to retrain, to resimulate or retrain the models. The first adopters of this technology and the typical companies that we are working with today are companies within the space of manufacturing. So today we see business challenges that are very, very, very strong for this company. One of them is the need to move to a smaller lot size and therefore having a more agile design process that allows for more customization. Moving to a shorter release cycle, so for instance 2-year release cycles in the automotive industry, whereas it was more around 6 years before. A very strong competition at all levels across OEMs and especially across suppliers of the automotive industry, but this is not only in the automotive industry. And the simulation capabilities that have been very well consolidated over the last few years, and that are a very good and important stepping stone for going to the next level, which is engineering intelligence. And the technical response provided by engineering intelligence is the ability to get instant feedback on design performance for any designer, to get guided towards better design options, and to explore a much wider design space than was before available. And this technology is being adopted and by a growing base of users and companies across the world. So I started the presentation with an example in the sports domain, and here we'll continue with another sports example, which is through our collaboration with the team SPAT, a Swiss team developing a new board concept aiming at breaking the sailing speed world record next year. And this team is working on a very interesting and ambitious concept of hyperventilating hydrofoils, which poses a strong challenge in terms of optimization and coupled optimization between fluid dynamics and structure. And they're using the neural concept platform in order to couple predictions from, to couple simulations from Abacus on the structural side, from Fluent on the fluid side, and trying to really push further the limits of what is possible with the concept of hyperventilating hydrofoil. And we really wish them all the best of luck for their world record attempt next year. Thank you for listening to my presentation. I hope you can follow Neural Concept in the future, or get in touch with us using all the ways available on our website. Thank you.